Hey everyone, welcome to the next video from Chapter 7. So in this video, we're going to start getting into doing the calculations that are going to lead us to how we solve these problems. So we're not quite there yet. We're not going to start solving until like tomorrow, but we can start looking at the sort of basic stuff we're going to need to solve these problems and the basic theory we need of matrices to solve these problems. It's going to be a lot more complicated than the theory we did last time though, thankfully. So we're talking about we're going to look at straight line solutions and end up talking what are called eigenvalues and eigenvectors of matrices, which are the things that we need to look at in order to start solving these problems. So let's go ahead and start talking about these straight line solutions. So we're going to start with a homogeneous first order linear system. So we have our system looks like x prime equals a times x. In this case, we're going to assume that A is going to be a constant coefficient matrix. So it's just going to be A11, A12, A21, A22. And also here, we're going to restrict to a two-component system. We're not going to do anything fancy with higher orders yet. Just two functions, and that's our A right there. Now, in some sense, this equation is autonomous. Right? What was our definition of autonomous before? It was just that the right-hand side did not depend on t. Well, here the right-hand side, again, does not depend on t. It's just a matrix times our x value. So when solving autonomous equations, getting an idea for what would happen, we started by looking for nice solutions, namely constant ones, and then built things up from there. So let's start by looking for some nice solutions. And constant solutions are good, but in this case they're not great because it doesn't really tell us too much. What we can do is we can look for solutions that stay in a straight line. The only way they move is in a line through the origin. Now, if my solution is going to move only in a straight line through the origin, what has to happen? Well, let's look at, so wherever it starts, let's say it starts here. If it's only going to move along this line through the origin, what has to happen? Well, its derivative has to be in the same direction or opposite direction of the point where it starts. That's the only way it can stay along that line. So for it to do this, for a solution to do this, it must satisfy x prime equals some multiple of x. Hint, r, we're going to be solving stuff again pretty soon. But I need to satisfy x prime equals r times x for it to move in a straight line through the origin from where it starts. So let's see what this looks like here. Because we know x prime is a times x. So this tells me that a times x must equal r times x, which if I transfer this into systems of equations, tells me that a11, a12, a21, a22, x1, x2 equals r times x1, x2, or a11 x1 plus a12 x2 equals rx1 from the first row. a21 x1 plus a22 x2 equals rx2 for the second row. And now I want to rearrange this and then recollapse it to matrices. So if I rearrange this, this gives me a11 minus r x1 plus a12 x2 equals 0. a21 x1 plus a22 minus r x2 equals 0. Or in matrix form, a11 minus r, a12, a21, a22 minus r times x vector equals 0. Now, I already know that if I start at 0, I stay there forever, so I'm always on a straight line through the origin from my starting point. So what I want is I want a non-zero solution to this equation, right? In order to find a straight line solution, I want a non-zero solution to this equation. And so we talked about this a little bit when I was talking about invertibility. So if I want a non-zero solution, I need something else to be true. So I want the determinant of a11 minus r, a12, a21, a22 minus r to be 0. right? If my determinant is not 0, then I cannot have a non-zero solution to the equation. So if I want something that's non-zero, I better make this be 0. And if I write that out, that is going to be a11 minus r, a22 minus r, minus a21, a12, or if I expand it all out, r squared minus a11 plus a22 r plus a11 a22 minus a21 a12 equals 0. And this here is called the characteristic equation of this matrix. It's the characteristic equation of the matrix and of the ODE system sort of as a whole, because since they're kind of the same thing. So this gives me two values for r. Again, there are three cases for what these two values can be because it's a quadratic equation. So option 1 is two real and distinct values. Option 2 is complex conjugate values. And option 3 is a repeated root. And over the next couple sections, we're going to be handling how to solve it in all these different cases. So this will be 7.5, this will be 7.6, and this will be 7.8. How to handle all these different cases. Now, this R is called an eigenvalue for the matrix A. Such an R is called an eigenvalue for the matrix A. And a vector x so that a11 minus r, a12, a21, a22 minus r times x equals 0 is called an eigenvector for that eigenvalue. An eigenvector corresponding to eigenvalue r. Basically, to get the eigenvectors, you just solve the system of equations. When you do that, you're going to end up with a free parameter. Just pick it to be 1 or something that's nice, and solve out from there. Now, what we see of this is that eigenvalues and eigenvectors give us straight line solutions to our ODE, and we'll see how in the next section, which is the place we can start to then sort of sketch out solutions from there, like we had our equilibrium solutions for our autonomous equations before. We can use these guys to give us a starting point for drawing out a sort of phase portrait, a picture of what the solutions look like for all values. All right, so I'm going to give you a problem now to solve for eigenvalues and eigenvectors of a matrix. If you want, you can look at the example in the next video, which is going to have a full example worked out for doing this before you do this, but take a look at it. I'm going to post that problem up for you right now. All right, so there's that matrix. I want you to find the eigenvalues and corresponding eigenvectors for this matrix. If you want an example first, take a look at the next video, which will have one of those in it. So that's it for this one. Thanks a lot for watching, and I will see you in the next video.